So, welcome guys to this video. We are going to be talking about exact ODEs. So, whenever we are given an equation in this format, this one is quite different, but we are going to transform it into something that looks the way you might be familiar with. So, we are going to be given an equation in this form, m, which is a function of x and y, dx, plus n, which is also a function of x and y, dy, equals to 0. So whenever we have an equation like this, the first thing you're going to check is if it is exact or not. If it's exact or a non-exact equation. Today we are going to be talking about exact equations, but anytime you see an equation like this, you always have to check if it is exact first. So looking at this, what do we do to check if it is exact? We are going to differentiate this m part. I can write this as m dx plus n dy equals to 0, where both m and n are functions of x and y. So you are going to differentiate partially. You are going to differentiate m with respect to y. You know the x is here before. You are going to differentiate it with respect to y. Then you are going to differentiate n. You differentiate n partially. Differentiate n with respect to x. So how do we know if it is exact? Exact means both of them must be exactly the same thing. So the m dn the m dy partial differential of m with respect to y must be equal to partial differential of n with respect to x. So let me use this first example as a case study. We have x y prime. Don't forget y prime is the y dx plus y plus 4 equals to 0. So what are you going to do? The first thing is to multiply through by dx, right? So we are going to have something like x dy. You know the y dx is what is here before. So if I multiply this part by dx, the dx down here will cancel out. Let me write it out. X dy dx plus y plus 4 equals to 0. So if I multiply everything through by dx, this will now be dx. Everything here too will now have dx. 0 times dx is 0. So this part will cancel out and we have x dy plus y plus 4 dx equals to 0. So we're now going to check if this is exact. How do we check? We differentiate this with respect to x. We differentiate this with respect to y. Now let's find our d. This is our m. This is our m. This is our n. This is our m. The one that carries the x is our m. This is our m dx. Don't forget addition is associative. You can just transpose it anyhow. You can transpose it anyhow. Now let's do this. So we are going to have the m dy. Let's check our dm dy. Differentiating this with respect to y. Y plus 4. If we differentiate y plus 4 with respect to y, we are going to have 1. Let's do the n dx. This is our n, which is just x. If we differentiate x with respect to x, we also get 1. Since our dm dy is equal to dn dx, this means this is an exact ODE. So what do we do next? So after checking if an ODE is exact, the next thing you are going to do is to integrate across. Now we have an equation. This is the exact equation we are working with. What you are going to do is to what? Integrate across. The solution of an exact ODE, let's say it is u, which is a function of x and y. U, which is a function of x and y, equals to the integral of m dx plus our constant, which is a function of y. Do you get what I'm saying? This is the solution to an exact ODE. The other solution is also n dy, integral of n with respect to y, plus c, which is a function of x. How do we know? In this part, the x, we are integrating with respect to x, which means y is a constant. So our constant will be a function of y. If you are integrating with respect to y, it means x is a constant, which means our constant will be a function of x. Now let's use the first question. This is our solution. These two, they are the solutions because they are going to be the same thing. Since our equation is exact, these two will be the same thing. They will give us the same answer. If we do not get the same answer, we are going to compare both of them to bring out a single solution. Let us work with the first one to find a solution to the first question. So we are integrating question number one. I will write it as in form of m dx. So we are going to have something like x dy plus y plus 4 dx equals to 0. I hope you understand how I got this. I have explained this before. So we are going to integrate across to get our answer. So when we integrate x with respect to y, integral of n dy equals to integral of x dy, and this will give us xy plus a constant. Our constant here is a function of x. Xy plus constant of x. Now if we integrate m dx, this part, we are integrating y plus 4 with respect to x. Everything here is a constant, which means our answer is x into bracket y plus 4 plus our constant, which is a function of y. We are integrating with respect to x, which means y and 4 are both constants. Y is a constant, 4 is also a constant. So everything here is a constant. So I'm just going to add, it's just like saying I'm integrating a constant with respect to s. So we just do cx, abi? So integrating a constant with respect to s just means you should add x to it. So we open this bracket and we get something like, so we are going to get xy plus 4x plus c, which is a function of y. So what do we do next? We compare what we got here, the answer we got here, and the answer we got here. And what do we see? Xy is in both of them. So basically, xy is part of the answer, xy plus the constant of x that we are looking for. We check it here and we find it here. This is the constant of x we are looking for here, and it is 4x plus 4x. Then the constant of y we are looking for, there is no constant of y here. There is no function that is a constant of y here. There is no function here that is a function of y and is a constant for this one. So it means this c of y, this constant which is a function of y, does not exist. So it means this is our final answer. Xy plus 4x equals to the integral of 0, which is a constant, equals to c. And this is the final solution to our exact ODE number 1. So I can write this as x is factoriable. X into bracket y plus 4 equals to c. Y plus 4 equals to c over x, which means y equals to c over x minus 4. And this is the final answer. I can also write that cx minus 1 plus minus 4. And this is the final answer to my ODE number 1. So I have successfully solved question number 1. Going to the second one. I hope you understand.
Yes, sir.
Going to the second one. We writing this. We have our m dx equal to this 2x sine 3y dx, and our n dy equal to 3x squared cos 3y dy. So what do we do? The first thing you always do is to check if it is exact. If it's not exact, you cannot work with it. What you have to do is to introduce an integrating factor. So we have to check if it is exact. So the first thing we do is to differentiate m with respect to y. Then we have to differentiate n with respect to x. If they are the same thing, if you get the same thing, that means the equation is exact. So the first one, differentiating this with respect to y, it means x is a constant here, and we are differentiating with respect to y. So x is a constant, 2x will stay where it is. Now let's differentiate sine 3y. We are going to get 3 cos 3y, right? 3 cos 3y. 3 is going to come as chain rule. So now let's differentiate this, the second one, with respect to, we have differentiated m. Now let's differentiate n with respect to x. With respect to x. So what we are going to get here is our y is a constant here, so we can still write it out. Cos 3y dot is a constant. Now let's differentiate this. We are going to get this is coming down 6x. If I write this out with my algebraic function first, I'm going to get 6x cos 3y. If I write this out with my algebraic function first, I also get 6x cos 3y, which means these two equations are the same thing, and which means this initial equation is an exact ODE. So what do we do next? We have verified that it's an ODE, right? So we are now going to find the solution to that ODE. So the solution to the ODE is that we integrate m dx, we integrate n dy. So it means the integral of this side must be equal to the integral of this side. Let's integrate this. I mean, we're integrating across, please. We are integrating everything across. So the integral of 2x sine 3y with respect to x, we are integrating only the x part. The y part is a constant. So I'm writing it out first. Sine 3y dot. Now let's integrate 2x. If we integrate 2x, we get x squared, right? We get x squared plus, since we are integrating with respect to x, y is a constant. So our constant is a function of y. For this part, we are integrating with respect to y, which means 3x squared is a constant. We are integrating with respect to y. 3x squared is a constant. So this means if I integrate cos 3y with respect to y, I'm going to get sine 3y over 3, right? I'm going to get sine 3y over 3 plus the constant, which is a function of x. Since I'm integrating with respect to y, the constant will be a function of x. This will cancel this out, and the integral of this becomes x squared sine 3y. So what do we need to do now? We compare and contrast both of them. The answer we have gotten. This is sine 3y x squared. This is x squared sine 3y, which is basically the same thing. But you will notice that the constant of y we are looking for is not present here, and the constant of x we are looking for is not present here, which means both of them do not exist. So our answer, our answer, which is a function of x and y, is what? X squared sine 3y equals to the integral of 0 is a constant, which means sine 3y equals to cx minus 2. I'm bringing x squared to the other side, which means sine 3y equals to cx minus 2. I can now write 3y equals to sine inverse of cx minus 2, and y equals to 1 over 3 sine inverse of cx minus 2, and this is the solution to our ODE number 2. This is the solution to the second exact ODE. Now going to the third question. We have x inverse dy minus x minus 2y dx equals to 0. So we can write out our m dx. Our m dx equals to this part, minus x minus 2y dx. Our n dy equals to x minus 1 dy. So now let's check if it's exact. The first thing first, differentiate n with respect to y. Differentiate n with respect to x. Now let's check if it is exact. If we differentiate this with respect to y, this function with respect to y, what are we going to get? Which means everything here is a constant. Minus x minus 2 is a constant. So we are differentiating y. If we differentiate y, it's going to disappear. So this is our differential of m with respect to y. Now this one, if we differentiate this with respect to x, we are differentiating 1 over x. We are differentiating 1 over x. Yes. So if we differentiate minus, don't let me make the work harder. X minus 1 is also okay. If we are differentiating this with respect to x, minus 1 is going to come down, right? Minus x minus 1 is going to give another minus 1, minus 2. And this shows us that what? Minus x minus 2 minus x minus 2. This second and the third equation is also an exact ODE. Do we get? This third equation is also an exact ODE. That means we can now integrate across to get our solution. we can now integrate across to get our solution. So it means we are going to integrate m dx, and the integral of m dx is what? Integral of minus x minus 2y dx. So this means y is a constant. We write it first. If we integrate minus x minus 2, what are we going to get? We are going to get minus x minus 2 plus 1 over minus 2 plus 1 plus our constant, which is a function of y, since y is a constant here. So we are going to get something like y, this is minus 1, which means it will cancel out this. X minus 1 plus our constant, which is a function of y. Now let's integrate n with respect to y. This is the integral of n dy is x minus 1 or 1 over x. Let me write it as 1 over x. 1 over x, or so it will not confuse us. X minus 1 dy is the same thing as saying integral of 1 over x dy. Yes, 1 over x dy, which means it does not even matter since we are integrating with respect to y. That means this x is a constant. So this does not matter. So I can now say my answer is x minus 1 is a constant. We are integrating with respect to y, so y will just appear. Since if we do integral of dy is what? Is y. Abi? So this means we have x minus 1y plus our constant, which is a function of x. So we are now going to compare and contrast. We have gotten x minus 1y here. We got yx minus 1 here. They are basically the same thing. If I write this in this way, if I write it and bring my y here plus c of whatever, they are basically the same thing. So it means my constant, which is a function of y, does not exist here. It does not exist at all. And this one does not exist at all as well. So my final answer, u, which is a function of x and y, is what? X minus 1y, both of these constants do not exist, equals to, if I integrate 0, I get the constant. So this is y over x is the same thing as y over x equals to constant, which means y equals to cx. And that's the final answer to the exact ODE. This is the final answer. So we have successfully solved the third question too. And the last one on exact equations that we are going to be talking about now. The last one. So we have question number 4. Our m dx is written in the form of 2x ln y dx. So this is our m, and our n dy is what? Y minus 1 x squared dy, and this is our n. So we first check if it is exact. To check if it is exact, we differentiate m with respect to y. Differentiating x with respect to y means x is a constant. So if x is a constant, I can write it out. 2x, 2x. We differentiate ln y. If I differentiate ln y, I get 1 over y. So this is what? 2x over y, or 2x y minus 1. Now let's differentiate n with respect to x. What do we get? We are differentiating this with respect to x, which means y minus 1 is a constant. Is a constant. Now differentiate x squared, we get 2x. So I'm going to write my x part first. So I have 2xy minus 1. So if we are to compare, we are going to see both of them are the same thing. Therefore, this fourth equation is also an exact ODE. So what do we do next? We find our solution. How do we find our solution? We integrate across. Oh, sorry. I have m dx is this, and I have n dy is this. So we are going to integrate both of them, and both of them must yield the same answer. So if I integrate m dx, I'm integrating 2x ln y with respect to x, which means y is a constant. Ln y is a constant. Ln y dot. Now, if we integrate 2x, what do we get? We get x squared, right? We get x squared. If we integrate, yes, we get x squared plus our constant, which is a function of y. Now this we are integrating with respect to y, which means x squared is a constant. S squared dot. Now we are integrating the integral of y minus 1 dy is same thing as saying the integral of 1 over y dy. Now if I differentiate y, I get 1, which means my answer is ln y plus my c constant, which is a function of x. So if we compare both of them, we see they are also the same thing. That means the constant which is a function of x and the constant which is a function of y does not exist. So our final answer u is our final answer, which is a function of x and y, is what? X squared ln y equals to x squared ln y, x squared ln y, both of them do not exist, equals to the integral of 0, which is a constant. So we can now simplify this for y and say ln y equals to cx minus 2, right? Which means y equals to e raised to power cx minus 2. Some of us might ask, how did I get this? Although it's a very, so we just raise both to the power of e. These two will cancel out, and y equals to what? E raised to power cx minus 2. And that's our final answer. And hence we have solved 4 different ODEs, which are exact. Now, I would like to touch another part of exact ODEs. We have successfully solved everything here. So, the next thing I would like to talk about is, what if they give us a solution and say we should write out the exact equation? What if they give us the solution and they ask us to find? Coming? Let me write this out.
Oh, can you treat one of the answers you get earlier?
Yes, I should have left it. X cubed y plus cos 2x equals to a constant. The second one, x e minus 2xy equals to a constant. Should I keep it 3 or 4?
3 is okay.
3 is okay.
Too safe.
And x equals to c tan y. So we are given, let's say we are given something like this, and we are asked to write out an ODE using each of these. How do we do that? The first one, we have x cubed y plus, this is our u. That's our u, which is a function of x and y. Now there's one thing we have to know. M is partial differentiation of u with respect to x, right? That's m, which means m dx is what? Partial differential of u with respect to x dx. N is partial differentiation of u with respect to y, which means n dy is what? Partial differential of u with respect to y dy. This is called total differentiation. You differentiate both of them, then you add it together, then we are going to get m dx plus n dy equals to differential of whatever is. The differential of the constant, when you differentiate the constant, we get 0, equals to 0. So how do we go about this? Let's try the first one. So we have been given our solution, which is u. This is our u. So the first thing we get is our m dx equals to, we differentiate the u with respect to x. So this will give us what? Let's differentiate everything here with respect to x. So y is a constant. So if I differentiate this, I get 3x squared y minus, I'm differentiating this with respect to x, minus 2 sine 2x equals to 0. Now let's write out n dy. N dy is what? Du dy. And this is going to give us, we differentiate the same equation with respect to y, which means x cubed is a constant, equals to x cubed plus, so since x is a constant, this is a function of and x and it is constant, it means it is equal to 0. So x cubed equals to differential of the constant 0. So what do? We write it out as m dx plus n dy. That's just what we are going to write. So what we are going to do now is add both sides together. So we have 3x squared y minus 2 sine 2x Now, this was differentiated with respect to x dx plus x cube. Since this is the only one standing, x cube dy equals to, we differentiated this with respect to y. So we are writing it as x cube dy equals to 0 plus 0 is 0. So this is the ODE that we have formed out of this solution. Let me write it out. 3x squared y minus 2 sine 2x. This is the one we differentiated with respect to x. This is our m dx plus x cube dy equals to 0. So this is the solution to the ODE. This is the ODE, sorry. This is the ODE we got from this equation. So we can now go to the second one. We can go to the second one. So the first thing we do is what? Differentiate with respect to x. Call it our m dx. So let's do it like this. Let me write it out like this. M dx plus m dy equals to 0. So first, let's find m dx. Differentiate this with respect to x. So if we differentiate this with respect to x, we will see that both of them are functions of x and y, which means I'm going to use product rule. I'm differentiating with respect to x. So I'm using product rule. Differentiate x first. I have e minus 2xy, right? Plus, if I differentiate this one now, leaving x alone, x dot, now y is a constant, which means if I differentiate everything I said, I'll be left with minus 2y. Minus 2y is going to come down. Minus 2y e raised power minus 2xy. So I've differentiated this with respect to x dx. If I differentiate c is equal to 0, my equal to will be on one side. Plus, now let's differentiate it with respect to n. With respect to y, sorry. Differentiating this with respect to y is only one simple equation. Since x is a constant, we are differentiating everything here. Y, we are differentiating with respect to y, which means x is the constant here. Minus 2x is the constant here. So it means minus 2x is the one coming out now. So I have minus 2x is the one coming down. With the x that is already down before is a constant, it turns into square. Minus 2x squared e minus 2xy. We differentiated this with respect to y. Everything equals to 0. So this is my m dx plus, now let me simplify it please. E raised power minus 2xy minus 2xy e raised power minus 2xy dx. This is the one we differentiated with respect to x dx minus 2x squared e minus 2xy dy. This is one we differentiated with respect to equals to 0. So this is our x, this is our m dx minus plus n dy. N is the one carrying this minus, it's not the equation. N is the one carrying this minus plus n dy equals to 0. So this is the equation we are going to get from the second general solution. This is the only we get. And for the last one, don't let me clean this. For the last one, we have m dx plus n dy equals to 0. So looking at this, differentiate everything, or let's bring tan y to the other side first, so as not to cause, it will not cause anything, but let's bring it to the other side. We have tan x over tan y equals to c. So I can write this as tan x, if tan comes up, it becomes cot y equals to c. So we are going to first differentiate this with respect to x, which means cot y is a constant. So I have cot y equals to 0. Cot y differentiated with respect to x. Cot y dx, right? I differentiated this with respect to, cot y is the constant, which means I will be differentiating tan x. If I differentiate tan x, I get sec squared x. I've differentiated this with respect to x. Now, about my n, I'm differentiating this with respect to y now. So it means tan x is a constant. Tan x is a constant. Now, if I differentiate cos y, I get minus cosec squared y equals to, now I've differentiated everything here with respect to y. The y equals to, if I differentiate from my constant, I get 0. So it means I have sec squared x over tan y, or I can just write it as sec squared x cot y dx minus tan x or let me write cosec square first, minus cosec square y tan x dy equals to 0. Now this is the ODE we get from the third equation. From the third equation, this is the ODE you get, and that's the solution to, that's the ODE we get from each and every one of them. And that's all about exact equations. So with this video, I hope you are going to be, let's say next time you find an equation that you're asked to solve using all these methods, you'll be able to do so. And that brings us to the end of the video. Make sure you like, share, and subscribe. Thank you. And that's all.